Hi and good afternoon. The title of my talk today is Unfair AI and Making AI Fair. So this is planned for around 50 minutes, so we will have some time for questions in the end. So let me just get started with the talk. So let's first look at data science and AI. So most of this talk is focused on data-driven AI, which is like largely the mainstay of AI in these times. Earlier, when data science used to be less popular, it used to be used with tasks such as handwriting recognition. So the task of handwriting recognition is like this. So you have somebody who has written some text in a piece of paper, and you take a picture of it, and you would like the machine to identify what is written in that piece of paper. So for example, here you have a transcript which is identified correctly by the machine. Whereas nowadays the task that we use AI for has significantly changed. Now, for example, we are currently using AI for very different kind of tasks like predictive policing. So what is predictive policing? Predictive policing is about making use of historical trends in various areas of the city, and making use of maybe information from CCTV cameras and stuff like that in order to identify potential crime scenes in a city. So what will you do once you identify these potential crime scenes? If you have somebody sitting in the police headquarters of the city, and then they can make use of this, and they can make use of predictive, they can make use of increased patrolling in those areas in order to prevent the crime from happening. So essentially, they're trying to reduce crime in the city by being proactive and predictive. So the difference between these two families of tasks is very stark and very sharp. The first one, handwriting recognition, is under the category of mundane tasks which humans would not like to do. And so it's about automation of mundane tasks. Whereas in the second category of tasks, which is increasingly becoming popular, we are making use of AI in order to make substantive decisions affecting humans. So let's look at some other use cases of AI. Now, so one of the areas in which AI is being used heavily is about automating medical diagnosis. For example, here you can see one of the classical use cases of AI, where you are trying to make use of a picture of a skin lesion in order to identify whether the skin lesion is a simple benign blister or something like a malignant tumor. So this is one of those very nice tasks for AI, because typically when you have dermatologists looking at skin lesions, they don't really go into the context of it. Whereas if you complain about headache, you're being asked about the context, or if you complain about some stomach upset or something, you are asked about what you had, etc. Whereas in the case of dermatologists are making decisions on skin lesions, it is typically very less context sensitive. So this makes it a very nice use case for AI, in the sense that it needs to, the task is well defined. It's about taking a picture, identifying the skin lesion within that picture, and identifying what kind of skin lesion it is. And there has been a significant success in these kinds of tasks. For example, there was a paper in Nature, I think in 2017, which had this title saying the dermatologist level classification of skin cancer with deep neural networks. So it is claiming to be achieving dermatologist level accuracy. Another kind of task is what we saw earlier, that is of predictive policing. So here the police is not even visible at the scene, which is being monitored. So the police is sitting in their police headquarters and monitoring images from CCTV cameras, monitoring transactions that are happening, monitoring maybe other kinds of information that might be relevant to policing, and so on, and trying to make a decision as to whether you would want to send more patrols to that area, or you would want to undertake a survey of that area through other mechanisms, etc. So predictive policing has also been a significant use case for AI. And we have known that it has been used heavily in the United States as well as some parts of Europe, but it may not be as well known that it is even making inroads into India. For example, this is something from a news report which talks about the Delhi police making use of predictive policing through crime mapping. And Delhi police, as you know, is widely regarded as very advanced in the as very advanced at the national level, but also recently has come under a huge has come under scanner for convicting people needlessly and anti-minority targeting, etc., in the context of riots that happened earlier in the year, etc. So when the Delhi police is making use of these systems, we would need to, and you can see that it has reached our backyard, right? So we need to make sure that we know what is happening around us in terms of AI and its uptake in government systems. So another use case of AI is about automating population estimation. So here, what you would do is you want to do a frequent population estimation of the city. You don't want to wait until the next census to get the population estimate. So what you might do is you might take some aerial footages of some parts of the city and go into those locations and quantify the number of people. And in certain other locations, you're not going to the people. You just take the aerial footages. So you get you're making use of the patterns between the footages and the population estimates in other locations in order to do the estimation of population in areas where you don't want to do door-to-door surveying. So let's look at a simple illustration of data-driven AI. So you have training data, which is of this form, which is actually labeled by humans. So you have some CCTV footages, and maybe you take a sample of thousands of footages and get humans to label it. For example, the top image is a non-suspicious image. It's just a lady walking into a store, nothing suspicious about it. Whereas the second one is quite a suspicious image. You have a lot of people there, and there is a scene which looks like a crime scene, etc. And that seems like a suspicious image. So you would train a machine learning model, which is essentially a statistical model, and once it is trained, you give it a new footage, and that footage is labeled by the statistical model as either suspicious or not suspicious. In this case, it is labeled as suspicious. This is basically how it works, right? So let's look at the different ways of data-driven AI. And as you can actually guess from the title of my talk, I'm trying to take a very critical perspective of AI and looking at its assumptions that it uses and trying to analyze it from using a political lens, as it will become clear going forward. So data-driven AI, as we saw in the previous case, you're making use of historical footages which are labeled by humans and trying to make decisions about the future. So you are codifying the past. Patterns from training data are useful to make decisions on test data. That is an assumption that we're using while designing AI systems. And the training data is historical, and test data is generated after the model. So test data is not present at the time of the model, or otherwise you would have used it for creating the model in the first place. Your fundamental assumption is that history repeats itself. So historical patterns and correlations are useful to make decisions about the future. Is this a kind of a reasonable assumption? It is definitely a reasonable assumption when it comes to handwriting recognition. For example, if you have a handwriting usually doesn't change very rapidly. Whereas political processes don't work that way. New crimes emerge. Previous types of crimes disappear, no longer used, etc. So this is a problem. We'll see. We'll look at this more closely in going forward. And the second assumption that data-driven AI uses is that of generalization. You are generalizing from historical data, right? You're not just using the historical data, but you're generalizing from the historical data in order to learn what is called a statistical model. And the statistical model is of a smaller size than the cumulative data put together. So evidently there is some kind of generalization, some kind of abstraction happening. And usual models are parametric in the sense that they have a finite set of parameters which need to be learned values for, and and that forces, because as a finite set of parameters are usually much lesser than the training data size, it forces some kind of generalization. The model is learned to fit to the data, and the problem with this generalization is that dominant patterns tend to be represented better. For example, if you have a large population and there is a majority category and the minority category, and they differ in the kinds of patterns that they exhibit, then the majority category patterns are going to have a higher sway, because if you're only going to learn 5 patterns, you might learn 4 majority patterns and 1 minority pattern, because that is what will improve the fitness to the data. So the way you're training these things has some kind of bias by virtue of the generalization that is being used. So majority patterns would be well represented and some minority patterns may be totally disregarded. Let's look at data distribution, which is another source of problem in data-driven AI. Machine learning is typically known to get better when there is more data. So if you learn a diagnostic model based on predominantly male data, the statistical model will perform better for males. And unfortunately, when you get the historical training data, you typically have some biases in the recording process. So if you want AI to perform fairly over demographic groups, we need to ensure fair data distribution. However, if you do some surveys, or if you ask people to fill in some information, some demographic groups respond better than certain other groups. So you have a data skew, which means that the people who the demographic groups which are well represented in the data will get better results from the statistical model that is eventually learned. So this is often neglected. This data skew and distribution is often neglected in the eagerness to use all the data that is available. For example, there has been a recent study on facial recognition, face recognition, and it is seen that in face recognition settings, many a time you get data sets which are predominantly male, and that means that the systems that are developed out of that data set, or the systems that are trained out of that historical data, perform much better for males than for females. And I've occluded the names of the systems that we're using here, but predominantly every system has a significant bias towards males, in the sense that it is more accurate at determining the faces of males than for females, and the difference is significant. As you can see there, sometimes the difference is 20 percentage points, which is significant. So let us look at another aspect of it. Now we are looking at the design of the algorithm and the training model. The statistical model design is not straightforward. It's not a given, in the sense that you need to define how you would want to learn the statistical model, or what is the nature of the statistical model. And the nature of the statistical model is inevitably based on assumptions about the data scenario that you would be using it for. So assumptions might be various. For example, you might have assumptions that the object of a class can be identified through a sequence of attribute-based decisions, and that is the fundamental assumptions that you're making when you're training decision trees. So what decision trees do is they start from the root and make decisions one attribute at a time, and eventually reach leaves where the decisions are made at the level of objects. So objects of a class can be identified through a sequence of attribute-based decisions. That is an implicit assumption that is used in the decision tree learning process. And linear separability within the chosen attribute space is used as an implicit criteria if you are making use of SVM, the raw SVM without any kernel. And when you're using a CNN-based classifier, you're implicitly saying that you want to place a significant emphasis on localized patterns. And if you're using an LSTM or an RNN-based classifier, you're making an implicit assumption that sequential patterns are important. So you're making assumptions all the time when you're doing models, and we seldom ask us questions as to whether these assumptions apply equally well to different demographic groups. Many times these assumptions are only justified anecdotally, in the sense that the designer of the algorithm which in the case of many AI-driven systems is a young, affluent male sitting in some office in the Silicon Valley, and his or her his experiences go into influencing the decision, influencing the design of the model much more than others. So this is also an often neglected question. So the question is whether these assumptions apply equally well to different demographic groups. All right. So typically, people it would apply very well to the designer's demographic group, but not necessarily to everybody else. So what I wanted to drive home is the point that designing algorithms that are used to make substantive decisions affecting humans, whether it be population estimation, whether it be predictive policing, whatever it may be, it is about affecting humans substantively. And these algorithm design processes are intrinsically and squarely political, right? So it is actually a political activity. When you're sitting in front of the computer and coding up something in some place in the Silicon Valley, which would end up being embedded within an algorithm that is being used in the product of a company, which is then employed within a state police force for predictive policing. So all of these are intensely political activity. So I have a small excerpt from this very interesting paper called "The Ethics of Algorithms: Mapping the Debate," and this was from the Big Data and Society Journal in 2016. Algorithms are inescapably value laden. Operational parameters are specified by developers and configured by users with desired outcomes in mind that privilege some values and interests over others. So the design of the algorithm privileges some values and interests over others, and at the same time, operation within acceptable parameters does not guarantee ethically acceptable behavior either. So this is something that we need to understand, especially when you're designing algorithms for like government clients, etc., or within government itself. You need to be very careful about how these might privilege some values over others. So let's look at a very basic example as to how a bias in a very simple algorithm can potentially be very harming in real world use cases. So let us say that you have a class you have a class which is like a STEM class, science, technology, engineering, mathematics, etc., and which by virtue of being a STEM class, as is often the case, there is a predominantly male population. So there are 5 males and 2 females, let us say, but you're not looking at those gender. You take the marks and you want to improve the teaching for that class, right? So that is the intent. So what you would do is you take the marks and then compute the average, right? And the average here happens to be 65%, 64.28%. And you would want to try 2 intervention strategies, 2 learning improvement strategies, and try and see how the marks improve. So you try S1, which is strategy 1, on a class in 1 year, and you get an improvement in the average from 64.28 to 64.71, whereas you try another strategy which improves only a little lesser, 64.42. Which strategy will you adopt going forward for the 3rd year? So typically, if you look at it, you would say that you would adopt the first strategy, because inevitably it is giving you a higher increase in the average. But what if you had more data about the class? And let us say that the data about the class is about let us say that we are looking at the gender data about the class, and the gender data looks like this. So you have 5 males in the class and 2 females in the class. So it's a predominantly male-dominated class, as in the case of any STEM subject. And here you have associated, there is a one-to-one correspondence between the gender in the sex vector and the marks in there. And let us see what is happening here. Now, let us say that we, instead of computing the average, we are interested in seeing how the genders perform, or how the genders perform differently among each other, well, across the gender groups. And let us say that we compute the average. We compute 2 averages. One is for the males, 67.8. and the other one is for females, which is 55.5. As you can see, there is a significant difference, and this is often the case as well. So now you are evaluating S1 and S2. And let us do this averages or the gender group level for both S1 and S2. And if you look at S1, the male average is improved to 68.6, whereas the female average has slightly come down, only slightly, to 55. Whereas in the second case, the male average has decreased slightly, it is 67.2, not 67.8, whereas the female average has improved greatly. It has improved from 55.5 to 57.5, which is 2 percentage points. So this is a significant difference, and this also closes the gap between the male performance and the female performance in the class. So if you look at these things, if you look at this data, you might actually say that S2 is a better strategy to have, because it does not affect the male average so much. It only brings it up marginally, but it improves the female average much higher. So it is so you are kind of bringing about you are kind of trying to close the gender gap in the performance difference between males and females in this case. So you might go with the second strategy. So let us look at what we did wrongly while we decided that we would go in favor of the S1 strategy earlier on. So what we did was, we had a basic representation flow. A crucial determinant of performance is not being considered. We did not consider the gender vector at all. And there was also another modeling flow, which is that the distribution is not unimodal. Means are very good to summarize unimodal distributions when the distribution on either side of the mean are very reasonable. Whereas in this case, it happened to be not unimodal. It happened to be bimodal, where the females had a performance peaking at around the 55 mark, whereas the males had a performance peaking at around the 68 mark. So we did not look at the distribution, we did not look at the gender around it, and also we had an evaluation flaw, in the sense that we looked at aggregate improvements, and the aggregate improvements are biased towards a group because that group is dominant in the class. So if you make use of these, if you understand the scenario, if you understand the context better, and make use of that context and make use of the determinant of performance and try and adopt a strategy accordingly, you might make a significantly different decision, and the decision might be considered as fairer in a reasonable sense. So if you choose S2 instead of S1 due to the higher fairness of S2, we will settle with a lower improvement in aggregate performance. That is something that we need to keep in mind as well. For example, here the higher improvement is achieved by S1 because total average goes up to 64.71, whereas improvement achieved by S2 is 64.42. However, we are taking that small cost as a hit in order to achieve a higher degree of fairness, in the sense that this is closing the performance gap, the performance gender gap here significantly at this cost to a slight deterioration in the aggregate performance. So let's look at some takeaways from this simple example. Representations could hide pertinent information. If we don't choose to represent gender, we will never realize the problem. So this is extremely important when it comes to policy making. We need to look at the crucial determinant and discrimination and the facet of discrimination. Otherwise, we will never understand where we are losing out on fairness. And modeling could be biased as well. Assuming a unimodal distribution would be biased towards a majority group. And utilitarian metrics are not everything. Aggregate improvements are not everything. Aggregate improvements might be causing an increase in the gender gap, an increase in the performance gender gap, which is an undesirable fallout of that. So aggregate utility and fairness are often in tension. So I have here a couple of quotes. The first one is from Cathy O'Neill. So Cathy O'Neill had written a very interesting book called Weapons of Math Destruction, which I would really urge you to read if you're interested in understanding the politics of big data algorithms. So what you see is that I would argue that one of the major problems with our blind trust in algorithms is that we can propagate discriminatory patterns without acknowledging any kind of intent. As you can see from the earlier example, our intent was clearly to improve the aggregate performance, and we are making use of that intent and improving the aggregate performance, but in the process you are increasing the gender performance gap. So you're propagating discriminatory patterns gender performance gap as a discriminatory pattern, and you are deepening the gender performance gap without acknowledging any kind of intent. Right? So utilitarian metrics have come to be considered natural to optimize for machine learning, and those need to be criticized. I mean, there is very little criticism of them within the computer science and the machine learning community. But things are improving, of course. But let's see, there's still a long way to go. And the next one is a quote from Mahatma Gandhi, who talks about utilitarianism. So he talks about it within the context of his own anti-colonial political struggle, where he says that a votary of ahimsa cannot subscribe to the utilitarian formula of the greatest good to the greatest number. So he says that, we saw that utilitarian metrics such as aggregate good can hurt fairness. He's saying that it can hurt even the goals of ahimsa. So he will strive for the greatest. For the greatest good of all, the utilitarian he is talking about, and die in an attempt to realize that idea. So I just wanted to bring out the perspective that although there is very little criticism of utilitarian metrics in machine learning, there has been a widespread acknowledgement of the pitfalls of utilitarianism within the political and the social domains. So what is fairness? Let us come down to some details now, rather than talking at a high abstract level. And let us say that you come across this kind of a scenario. You're riding a motorbike and you come across one of our public buses, which is overtaking from the right hand side, providing very little room. This is definitely unfair. Why is it unfair? It is unfair because it violates the appropriate procedure of driving. It violates what could be called as procedural fairness. So the right procedure says that they should stick to their lane and provide enough room for the other vehicles on the other lane. So this violates procedural fairness. So what is procedural fairness? Procedural fairness is the institution of well laid out and appropriate process and conformance to that process. So in the case of machine learning, you are mostly making use of what could be called a similarity-oriented decision making. And what is similarity-oriented decision making? Similarity-oriented decision making often says that you should assign similar outcomes to similar objects. And this is also called individual fairness. And individual fairness is the predominant stream of procedural fairness in machine learning systems. So let's look at another condition, another type of fairness. So you might have seen, when the entrance results get announced, you will kind of come across these kinds of ads in newspapers. Here you have the listing of the toppers in JEE in some year. I don't remember the year where I picked it from. And as you can see, you have a number of people whose pictures are advertised, are part of the advertisement. And what do you notice very sharply about this one? And well, we're looking at it from the perspective of fairness, and as you can notice, all of them are male. Right? So most JEE toppers are boys. So JEE is procedurally fair, but the outcome of JEE produces a very significantly skewed result when you look at it from the perspective of gender demographics. So, and most MLAs and MPs are men. Unfortunately, we have some kind of affirmative action policies in the local body elections that is coming up in the next few days. But where we don't have such affirmative action policies, such as in the case of MLA, such as in the case of state legislative assembly elections, and the case of general elections in the country, most MLAs and MPs tend to be men. But this does not mean that elections are not procedurally fair. Elections are procedurally fair, or at least, I'm not a huge fan of EVMs, and I believe that EVMs violate some kind of procedural fairness. But if you're doing it properly, then elections might be procedurally fair, but might produce significantly gendered outputs. So this brings us to what is called as distributive fairness. Procedurally fair methods could still distribute rewards unfairly. So what is distributive fairness? Distributive fairness is about looking for representation balance and the equality of outcome. So people who are similar on task relevant attributes may need to be treated differently to ensure equality of outcome. For example, you might need to ensure that there are different thresholds for marks on different groups, and as is used in India's reservation system. So two people might receive the same mark, like say 36, but one of them might qualify because the group has a cutoff threshold of 35, whereas the other guy falls in a group where the cutoff threshold is 40. And you might institute certain policies targeted to level off the gender pay gap, and you might introduce certain policies targeted to enforce diversity in the workforce. So all of these are about distributive fairness. And the two notions, if you just summarize them, there is when you look at procedural fairness, you would like to eliminate disparate treatment. You would like to treat everybody equally, and you would like to have equality of opportunity. You want to ensure that procedure is fair. You want to ensure a level playing field. You want to ensure that similar individuals get similar outcomes. And it leads to what are called access or regulatory fairness. So you don't want to cut off some people from taking part in a test, for example, or attending classes to learn something. And these are also called individual fairness in machine learning literature. And in the case of distributive fairness, you are trying to ensure that the outcomes or the impact of the decision-making process is fairly distributed across groups. So you're looking at representation balance, and you might need to treat dissimilar people similarly to ensure outcome balance. And this is often called as group fairness in machine learning literature. And these two notions are not a computational notion. Distributive and procedural fairness are everywhere. Basically, fairness is a political question. So social reform of various kinds address one of these two kinds of fairness, or maybe a mix of both of them. I'll just just so that you understand that it's a politically important concept, and we are simply using it in the context of machine learning. I would like to highlight some examples here. So there was this person, the social reformer called Ayyankali in Kerala, of course, as you know, who voted for fair admission process. What he did was he was living at a time when people of certain castes could not attend school. So he said that unless this young lady over there called Panchami would be allowed into the classroom, I would ensure that all the farmers are kept out of fields. And we're talking about this in a time when farmers are in protest as well. So he was asking for fair admission process. And fair entry regulations were part of one of those famous struggles in Kerala, which was Vaikam Satyagraha. Here I have one of the prominent leaders of Vaikam Satyagraha, Guru, of course, and in the backdrop, against the backdrop of the Vaikam temple, of the picture of the Vaikam temple. So these are about fair admission processes, fair entry regulations. These are about procedural fairness. You're trying to ensure that everybody has access to the education, or everybody has permissions to enter a particular premises. There has been a lot of movements around the other kind of fairness, which is about outcome fairness. One of the prominent figures is about Bhimrao Ambedkar, of course, who the father of the Constitution, who instituted provisions for fair representation of SCs and STs, scheduled caste and scheduled tribes. And this person is not somebody whom many of you might know, but he was largely influential in progressive politics in the 20th century India. So his name is Mandal, and he was a former chief minister of Bihar, and he led a commission which was popularly known as the Mandal Commission, which was about ensuring fair representation of OBCs. So the first two, we talk about Ayyankali as well as Guru. They were looking at one of the illustrated movements here are about procedural fairness, whereas Ambedkar and Mandal were talking about outcome fairness within the government sector. So let's move on to some particular tasks in machine learning, and we'll take the task of clustering. So what is the task of clustering? Some of you might be familiar, some of you may not be familiar. You take a number of objects in a task-relevant representation space, and these could be, for example, let us say that you're trying to cluster flowers or something. Then these could be petal size on the x-axis and sepal size on the y-axis, etc. And you might want to do some clustering, which is about identifying groups of grouping these data into groups of objects, and each of these group have what is called a centroid, which is a representative prototype of that group. So you have clusters with prototypes, and this is what partitional centroid clustering does. And this is a very fundamental operation in order to make sense of large data sets. So if you have a data set in the order of tens of thousands, and you don't have enough human labor to be available to human labor that is available to look at each of those data objects, so then what we might do is to do some clustering, cluster them into maybe 100 clusters, and look at the prototypes of each of these clusters to understand the patterns in the data. So this is a very popular thing for exploratory data analysis. So let us look at individual or procedural fairness within here. So the procedural fairness says that you want to assign similar outcomes to similar objects, right? So here let us take the case of this top right object in the red cluster, and its closest neighbor happens to be in the blue cluster. And its own neighbors its own cluster members or its own neighbors in the cluster tend to be at a higher distance than the closest neighbor, of course, because that's the closest neighbor. And if you arrange these things, you would see that there is a significant difference here. This is the distance to the closest neighbor, and that is much smaller than the distance to the other neighbors in the cluster. Whereas this one is actually a violation of the individual fairness rule. So in the sense that despite these two being so close to each other, they are put in different clusters. The clustering violates individual fairness for this particular object by putting the red point and its closest neighbor in different clusters by assigning them different outcomes. So some amount of individual unfairness may be inevitable while allocating decisions based on a global criterion. So here you're trying to optimize for the global coherence of clusters. And when you optimize for the global coherence of clusters, some individuals might be subject to some kind of individual unfairness, right? So that is inevitable in many a time. And we need to make sure that this individual unfairness is a reasonable outcome of optimizing for the common good, that is a higher overall coherence of clusters. So that is how, this is how we can make sense of individual fairness within the task of clustering. So what we did in one of the papers recently, along with one of the PhD students, Savita, who actually happens to be a CUSAT alumnus as well. So what we did was to look at representativity fairness as a notion of individual fairness. And let us look at this, the example here. So you have 5 objects, 4 blue objects and 1 red object. And these colors represent the clusters to which they belong, and these are the cluster centroid. So this is the cluster centroid for the blue cluster, and this red cluster has its own centroid. And if you look at the distance to each object to its own cluster centroid, you will see that this is the vector that it looks like. So what you do by means of individual fairness, or by means of what we call as representative fairness, is to ensure that this cost or this vector is made as uniform as possible. And how can you make it uniform? In this case, you can make it uniform by changing the cluster assignment. By changing the cluster assignment, what you would get is a different metric, where here you have changed this object from belonging to the blue cluster to belonging to the red cluster. Now the cluster prototypes also change. So this one is the average of the objects, average of the blue objects, it is brought here, and the average of the red objects appears here. So if you look at this vector here, the highest number is 1.41, whereas this one has the highest number is 1.77. So here the distance of this object to its centroid is much greater than the distance of any object to its centroid within this configuration. So I hope I'm reasonably clear here. So the average distance, which is the average of these elements, is going up slightly, and that is the cost of fairness. But the variance within this vector is coming down significantly. The variance has come down from 0.4 to 0.19. So this is similar to what we saw in the marks example across gender categories. You are improving the fairness, or you are improving the distribution fairness across the gender groups, but there is a cost, which is that the average utilitarian measure, or the average takes us a little bit of a hit, right? So representativity fairness can be enhanced by changing cluster assignments. So let's look at group or distributive fairness in the case of clustering. So let us say that we have advertised a government job opening, and we've received several hundreds of thousands of applications, as is common in things like the Indian Railways. Whenever they advertise thousands of jobs, they get crores of applications. So what you might do is to do some kind of a clustering in order to reduce the load of looking at each of them. And what you might do is to look at is to group them into clusters and look at some cluster prototypes and make cluster level decisions. So all the applications coming into this cluster are excluded from consideration. Some of them are shortlisted, some clusters are shortlisted, and some of them are there is enough ambiguity, so you might want to look at it closely and see whether they need to be shortlisted or rejected. So what you might want to ensure here is to ensure that these clusters are have a fair distribution of genders. So if you produce these kinds of clusters, 7 males and 2 females in this cluster, if you produce these kinds of clusters, you are implicitly forcing the decision maker, the cluster level decision maker, to make gender aligned decisions. That is not what you want. That is a way of propagating bias. Whereas if you ensure that all of these clusters have a fair distribution of genders, like the case of this cluster where you have 4 males and 4 females, then you disallow the possibility of gender aligned decision making. Right? So you disallow the possibility, you ensure that among those shortlisted, if you shortlist 3 clusters, all 3 of them have 50% men and 50% women. The shortlisted, the entire shortlist also has 50% men and 50% women. So if you can ensure gender parity within clusters, you can ensure gender parity in any process that makes use of clusters to make cluster level decisions as well. So what we could do in order to do this is, like, let us say that we have these. Let's say that these are the objects, and let us assume that red is maybe one gender, let's say male, and blue is females. And if you do a simple clustering, you might get you have 50% representation of males and females in the entire data set. If you do a simple clustering, you might get a cluster like this: fairness agnostic clustering. You're not concerned about fairness. And what you would get is, in the cluster 1, you have 67% females or males and 33% females, and in cluster 2 you have the opposite. So how do you quantify the disparity brought about by this clustering? You can quantify it by comparing these vectors. You can compare 0.67.33 to 0.5.5 and get a quantification. So that is 0.17 square, the difference between this and this, plus 0.17 square, which is 0.0578, and similarly for this as well. And you get a cumulative fairness disparity of 0.1156. So this is the loss of, this is the lack, and this is a quantification of the lack of fairness in a given clustering. Whereas if you would want to improve the fairness of the clustering, what you might do is you might do a different kind of clustering, and that clustering might look like this. So what you get is you have 50% males and 50% females in the data set, and you have similar proportions, you have exactly the same proportions in cluster 1 and cluster 2. So if you count, if you measure the disparity here is 0, the disparity here is 0, so the fairness disparity is 0. But what you have lost in the process is that you've created slightly less coherent clusters. Earlier the clusters were nice and round. Here now you need to stretch the boundaries in different directions, slightly differently, in order to get in order to improve the fairness. So there are slightly less coherent clusters. So what we did in one of the other papers that we had this year, once again by two PhD students, Sabita and Soumya, what we did was to simultaneously optimize for clustering coherence and fairness. And essentially what we did was to do something like this. So you have cluster diversity and the fairness disparity. And you're trying to reduce the cluster diversity. You're trying to get more coherent clusters and also improve fairness. So you're trying to minimize the weighted sum of cluster diversity and fairness disparity. And there is a relative weighting, so you can set lambda accordingly. If you set lambda to a high value, you get much fairer clusters, but at the cost of less coherent ones. So let us look at another task, which is the task of outlier detection. And outlier detection is the task of identifying from a population from a population, you want to identify a small subset of people who are considered abnormal or outliers. So you might want to do some amount of checks on them in order to ensure that there is no illegality about what you're looking for. For example, financial transactions. If you find some abnormal financial transactions, you might want to scrutinize it further, and so on. So outlier detection is used in a variety of contexts. So what are outliers? Outliers was defined in this 1980 book, a monograph by T.M. Hawkins. So he defines outliers as an observation that deviates so much from other observations as to arouse suspicion that it was generated by a different mechanism. For example, here clearly the red fish is an outlier because it's traveling in a different direction as compared to the other ones. So outlier detection is often used in a variety of different processes. One is about insurance premium. So in many of the Western countries, your insurance is determined by your driving pattern. So if you drive reasonably and you're sometimes given a black box to put in your car, and the car and the black box uses GPS to track your driving, and if you drive reasonably, you get a lower insurance premium the following year. So if you drive abnormally, in terms of if you're an outlier, if you're regarded as an outlier, you get a higher premium. And it is often used in the case of visa applications as well. So those which are regarded as abnormal visa applications or outlying visa applications are denied many a time or scrutinized. And many a time it's also used in predictive policing applications, where if you find that there is some abnormal activity in a region, abnormal activity is also an outlier. If you find abnormal activity in a region, you tend to go and scrutinize it further. So when you automate outlier detection, is it the case that it implicitly is biased against some minority patterns or minorities? It might be, as I would argue in this slide. So identifying abnormality entails a modeling of what is normal. If you need to identify abnormality, you need to know what is normal as well. You need to identify what is normal. You need to have a model of what is normal. And many a time you don't want to determine what is normal, but you would let the data to define what is normal. And in that case, the model of the normal is the model that best fits the entire data. And when you talk about the entire data, you are talking about the majority category being benefited, as in the case of as we saw in the case of generalizations, right? So when you're trying to get a model which needs to be assumed to be normal, it is likely more influenced with the majority category since it's more prevalent. And this could lead to picking out minority demographic groups more frequently as outliers. So the bias in outlier detection can be illustrated visually like this. So if you have population ethnicities like this, so here you have a hugely majority, if you have a majority population which accounts for around 65% of the entire population, or maybe even slightly more, 65% of the entire population, and the minority categories are here. But when you do outlier detection, when you pick out maybe a small fraction as outliers and profile them in terms of their ethnicities, you typically see something like this. So the 67% majority population appears among the outliers only for like 40% or something. So there is a discounting of that population fraction in the case of the majority community, whereas a minority community, especially the minority community right here, it is heavily overrepresented in the outlier ethnicities. So if you have these kinds of distributions, it means that your outlier detection method is against minority ethnicities. So you would ideally want to have something like this as well in the case of outliers, right? So that is what we might want to ensure by means of doing fairness in outlier detection. So this is one of our papers where we did fair outlier detection, and I would like to also mention that this was predominantly the first paper in fair outlier detection. So we use this model of neighborhood-based outliers. In the case of neighborhood-based outliers, you are looking at an object and assessing it with respect to its close neighbors in order to see whether it's an outlier or not. You're looking at an object and assessing it with respect to its close neighbors. So here we are looking at the 5 nearest neighbors, and out of that 4 of them tend to be from the majority. 4 of them are from the majority community, and there are only 2. Well, that would obviously be the case. So essentially it is implicitly biased because the minority community objects compared with their neighborhood, and the neighborhood tends to be mostly majority objects because they are relatively more abundant. So what we do is we normalize the scoring by making use of the sensitive attribute membership. We discount the anomaly score of an object if it is getting predominantly compared to objects of other ethnicities, right? So that is what we do in our paper. I don't have time to get over the details, so I will just skip that and let you go into the paper if you would like to look for more information. So that is Fair Outlier Detection WISE 2020. So what are we talking about here? Just to summarize things. So data-driven AI is often unfair. This is of much concern while making decisions that impact individuals and societies, and patterns in data could be unfair. Design of algorithms could be unfair. So unfairness could come from the data itself or from the design of algorithms, and there are various varieties of unfairness. So fairness is not a one kind of model. There could be different kinds of unfairness. One could be procedural fairness, one could be outcome fairness, etc. There are other kinds as well which we have not gone through. If you would like the algorithm to be fair, we need to design for fairness. Unless we design for fairness, we will not get fairness. So fairness, that is because fairness is often in tension with accuracy and efficiency, and if you optimize for accuracy or efficiency, you tend to get less fair outcomes. And this is what we saw in the case of the marks example in one of the previous slides as well. So fairness in AI comes at a cost to utilitarian metrics such as accuracy and efficiency, and if we can achieve high degrees of fairness at low cost to accuracy, we can claim some success. So fairness comes under the broad umbrella of AI ethics. So if you look for AI ethics, and if you're interested in AI ethics, I would urge you to look at some of the literature around AI ethics, and you will find that most of the AI ethics literature talks about interactive ethics, in the sense that when you're dealing with robots, how do you want robots to be able to be treating you? Do you want them to be gentle and polite, or do you want them to be rude and mechanistic, etc.? And there are a number of items here, there are a number of considerations here, such as trustworthiness, interpretability, privacy, etc. So these are all considerations that come into the picture when you're looking at ethics in the interface of humans and data. You're looking at ethics in the interface of humans and machines, let us say. Whereas fairness comes under a different category of ethics. It is heavily normative. And what do you mean by normative? Normative is about asking the should kind of questions, asking what we should be doing, what is the right thing to do. So fairness is a heavily philosophical, political and normative concept, and in that sense it is highly different from the interactive fairness measures such as interactive fairness considerations such as trustworthiness, interpretability and privacy, etc. So I'm attempting to chalk out a difference. It's not a very well laid out difference, but I would like you to think about fairness in a very normative way rather than in the behavioral sciences way that is used when judging systems for trustworthiness, interpretability and privacy. And one of the bottom lines in this talk is basically that fairness is an intensely political concept, so you cannot take politics out of fairness. So it's a political activity as well to be designing fair algorithms. So I'll stop. This is my last slide. I will stop with a little story, and this is something that I've been looking at. I've been considering recently, but well, I mean, these are still in the consideration phase. I've not made any headway around it, which is about trying to make use of randomness as a way to enhance fairness. So let us say that you go. You go through some kind of a security screening system, and you are picked out at random to do a detailed check. You would not consider that as unfair, because as long as you're convinced that it is random, you would be okay with it. I mean, randomly picked me out. That's okay. I mean, it could happen. It could have happened to anyone. It happened to me. It doesn't matter, and so on. So randomness is a very interesting phenomenon, which inspires a lot of trust in us about the fairness of the system. So. Here, the picture that I have here is from a fishing village in the west of Kochi called Chellanam. So there they make use of randomness in one of their processes in a very interesting way. I would like to talk about, I will describe this in two lines in a story. So many a time when fishes, when they want boats to venture out to the seas in order to do fishing, they have a lot more people than the boats can accommodate, right? So if the so let us say that you have 100 people and the boats can accommodate only 50. So you would need to keep 50 people on the shore. And how would you do that? You would, if you allow 50 people to go in and fish and reap the benefits of it, you're being unfair because the other 50 are starving. The other 50 don't have a means of livelihood. So the fishermen of Chellanam have devised a very interesting procedure in order to address this problem. So what they do is they everybody assemble. So let's say that the 100 people assemble, and they pick 50 of these people using a process that has some randomness in it. It's not a completely random process, but it has a significant amount of randomness. And you keep the other 50 people on the shore. So these 50 people are staying on the shore. And when these 50 people have gone to fish, come back, I mean, it's not 50, obviously, I'm just using a number here. And these 50 people go off to the seas and come back with a catch. They share it largely equally across the people. And there's the people on the shore get notchless, but it's mostly equally. So in that sense, what it means is you're creating a random process in order to allocate who goes into the boat. So well, eventually over the course of 10 days, everybody would get 5 days on the boat and 5 days on the land. All right, but you will get the catch on all 10 days. You are sharing the catch kind of equally across all those 10 days. So this is very innovative mechanism used in Chellanam as well as certain other fishing villages. Certain other fishing villages have different kinds of randomness, and I can send you the link to this Chellanam story if you're interested. But this is a very interesting way of using of a mechanism to embed fairness through randomness. So I'm looking at ways of so random number generators have been used in computer science for quite some time, and I'm looking at ways of how we can use that in order to achieve higher degrees of fairness in machine learning algorithms. So I'll stop with that story, and hopefully we can address a couple of questions if we have time. Thank you very much.